Hey, what's up, guys? Yeah. So today I'm going to talk about the famous theorem called the Valiant Vazirani, and why I want to talk about this theorem, because this is the first step that leads to total theorem, and I think it's very interesting. So I want to make my own video and describe the proof. Okay, hope you guys subscribe to my channel. Okay, so the proof is very long and it's not very difficult, but there's a step by step. There's a few steps. Okay, so let me just say the theorem. So theorem says that there is the probabilistic uh, polynomial time algorithm A, such that for every Boolean formula, so this is a Boolean formula, phi, that okay, so this Boolean formula has a variable x1 to xn, and let's say phi is a set. Phi belongs to set. So phi belongs to set means basically means that phi is satisfiable. So there is a satisfiable assignment. Phi of x is output 1. Then the probability is a random probability in this algorithm, right? So a phi will produce another Boolean formula. So this Boolean formula belongs to a unique set. So belongs to unique set basically means that there's only one solution, has high probability, 1 divided by an. And if I do not belong to set, then the probability that a phi belongs to unit set is 0. Or simply speaking, the number of a phi solution, the number of the solution of a phi. Let's not use this. So this means that the probability of belongs to unit set is 0 if phi do not belong to set. If phi belongs to set, the probability of a phi belongs to unit set at least have one solution, has uniquely one solution with high probability 1 over an. Okay, so once you have this, then basically you can say that NP, right? Because we know that set is NP complete. So this implies NP can be reduced to RP because only one side, right? So RP is basically if X belongs to L, the Turing machine is set with probably high probability, and if X do not belong to L, then reject, always reject. So it's always reject with high probability. This 1 over an can be amplification using arrow amplification with the unique set, so U set, and the U set can be reduced to the parity P. Okay, so yeah, so the parity P basically tell you that the basically parity P is basically if your solution either have 0 or 1, this parity P. So parity P will give you will output the number of the solution to be even or odd, right? Simply speaking, or be even or odd. But since your solution is either 0 or 1, then you can just use this parity P to replace by unit set. Oh, sorry, the unit set can be replaced by parity P. Okay, because this parity P will output either 0 or 1. Okay, this is odd, this is even. But your unique set has only has either 0 or 1 solution. So this is also BBP to the parity P. Because RP is just one side arrow, right? BBP has two side arrow. So RP is a subset of BBP. Okay, so this is the first step. And so I should say A phi is either belongs to unit set or not. So A phi is high probability to be only have one solution or high probability with 0 solution if X is phi do not belong to set. Okay, so once we have this, then this is the statement. So we can start to prove. And the proof very lengthy, so I think I would like to say some lemma. So the first is lemma 1. This is the simple one. It's basically some probability. This is called exclusion inclusion lemma. or basically inclusion or exclusion lemma. Okay, I think this is simple. Right, so let's say you have some AI where I from 1 to n, or basically I from 1 to n, right? So so the probability that the union AI, so I should say union I from 1 to n is greater or equal to summation of probability of AI I from 1 to n minus I less than j probability of AI intersection aj. So this is the lower bound, right? And the upper bound, we should use the union bound. So this is a very powerful technique that if you know probability of AI and aj and also their intersection, then you're able to bound the union and for upper and the lower. So this is the union bound. This is called union bound. Well, I think everyone knows about union bound, so I would like to prove the first one. Okay, so the first one, let's say just do the mathematical induction. So I would say n equals to 2. It's a very simple exercise, right? You know probability of A union B is probability of A plus probability of B minus probability of A intersection B, right? So it's trivial, it's equal, okay? And then let's say n equals to 3. So you have probability of A union B union C is basically the probability of A B C minus probability of A union B, sorry, intersection B, A intersection C minus probability of B intersection C plus probability of A, B, and C, right? So if you neglect this, then you get greater or equal to probability of A, B, C, and the probability of A, I, A, J, let's say sum of I, J, 1 to 3. Okay, so which we prove that so we know that simply speaking, this is true for n equals to 2, n equals 3. So let's give you a hint that how should you prove this. Okay, so proof basically use mathematical induction. And right, so I can say n is true, right? So I can say that the probability of union of AI I from 1 to n is greater or equal to summation of probability of AI I from 1 to n minus the I, J, n and 1 probability of AI intersection AJ. Okay, so now let's consider you add the term called an plus 1. Oh, sorry. What's going on? Okay, so you add a term. Okay. So I want to compute the probability of union of AI I from 1 to n plus 1. And I want to use I imagine that this is a tilde union an plus 1. Right? So a tilde is just union of AI I from 1 to n. Okay, so this is probability of a tilde plus probability of an plus 1 minus probability of a tilde intersection with an plus 1. Probability of a tilde, then I can use this lemma, right? So I can just use this lemma. So it's greater or equal to summation of probability of AI I from 1 to n. And I can combine with this one, like a plus 1, right? Minus okay. So this is okay, so this term is basically the union of AI I from 1 to n intersection with an plus 1. Right. This term can be reduced to probability of union I from 1 to n AI intersection with an plus 1. Okay, and this term can be used union bounds, right? So this term is less or equal to summation of AI an plus 1. Okay. So the first term is exactly here. The rest, this term combined with this term. So this term I can replace to I from 1 to n probability of AI intersection with an plus 1. So combine these two terms, exactly what we want. Right? We get I from 1, j n plus 1, probability of AI intersection with AJ. Okay, so finish the proof. Yeah, so this lemma is as simple. It's not related to just simple probability. Hopefully, it's not so difficult. Okay, lemma 2 that I'm not gonna prove in this video because it's a little bit complicated. So this is called the pairwise independent hash function. Okay, so simply speaking, such set exists. Okay, so what kind of set? Okay, so you have a set H, and each element H belongs to H. Set is a function from 0, 1 to the n bit string to k bit string. Let's say k greater than A. Okay, and satisfy say it should be greater than 1. Okay, so has the following consequence. The first one is that H is computable. H is efficiently computable, so H can be computed in poly n time. So given X, right, you can compute H of X easily. Okay. And the second one is that if you randomly pick, so for every X belongs to the bit string 0, 1 to the n, if you randomly pick H, small h in capital H, you can ask what's the probability that H of X is output 0 to the K. This guy is basically, let's say 1 to the 2K, okay? And if you take any two different X and Y, and you want to ask what's the probability that you take the same H. Okay, so you take same H, and then you such H of X equals to 0, H of Y equals to 0. If two of them both happen with the two, so it's pairwise independent, 1 divided by 2 to the 2K. Okay, so the idea is that you believe, at least in this video, you believe that such H exists. Okay, so this H exists. Okay, so once you have this H2O and this probability 2O, then with this that you are able to hopefully you are able to prove this Valiant Vazirani theorem. So let's go through a proof. Oh, so proof, the idea is the following, right? So you start from phi, right? And then you want to construct some random guy, right? So phi may have many solutions, but I want to hash the solution such that the solution only map to 0 Ki, and I accept. So simply speaking, that given a phi, right? I let's say I do phi end with the CH. Okay, so CH is a formula. Okay, it's a formula such that the output true if H of X is 0 to the K, and output false. And if it's not 0 to the K, then output false. Okay, and since H is efficiently computable, right? So H is in poly, and the poly is in P/poly. So I can translate polynomial computable function into the I create a polysize circuit. So I put polysize circuit here. Okay, so this I translate to phi into phi of X and C of HX. Okay, so obvious that if phi is unsatisfiable, the number of solutions is 0, then you immediately apply that the number of solution of phi and CH must be 0, right? Because since there's no solution such that phi is true, right? So if phi cannot be true, then anything end with anything, the false end with anything must be false. Okay, so it must be false. Okay, so it's trivial, right? So it's trivial that we already proved this. Okay, so a phi just phi end with some random function h, random hash function, random hash pairwise hash function, pairwise independent hash function. Okay, so the rest is proof so you need to prove that the probability of phi and ch has high probability with only one solution. Okay, so here comes the probably the most difficult part. Okay, so in here that I first assume that the number of solution S is basically less or equal to 2 to the k minus 1 and greater or equal to 2 to the k minus 2. Or then h, I choose h to be 0, 1 to the n, to be 0, 1 to the k. Well, the reason will come true. Very easy. Okay. So if you randomly choose h belongs to h and put ch here, then the number of phi and the ch will be a random variable. Because you randomly pick h, so ch will be a circuit. So phi and the ch will be a random variable depending on the random h you choose. So this guy random variable. Let's call this guy n. Okay. So I want to ask the probability of n equals to 1, right? Exactly. So the probability that n equals to 1 can be computed by probability of n greater or equal to 1 minus probability of n greater or equal to 2. Okay. And the probability of n greater or equal to 1 is basically computable by our lemma, right? So, right, n greater or equal to 1, I can define a AI, right? I can define AI to be or AH. Okay, so AH is the event. Okay, AH is an event. What kind of event? AH is an event. Oh, I cannot change the color. Well, okay, so AH is an event. Let's say this is event that yeah, that's if AH is an event. Let's say event what? Event that h of x is 0 to k. Okay, so AH is an event that h of x is 0 to the k. And let's see. And yeah, okay. So AH is an event that f of x equals 0 to k. Okay. So now right. So now I can n greater or equal to 1, right? Basically what? So what this means is that probability of union of h belongs to h, but not only this, right? You need to consider x belongs to s, right? Because in order for this, AH is this guy, right? But you need to, in order for this guy to be satisfiable, ch must be 1 and ch must be true, and the phi also must be true, right? So our n is actually union of n greater than 1, just a union the events that AH, the probability events that for each h belongs to h, but only x, and also fix x belongs to s. Okay, so you compute this guy, and when we use our bound, right? So this is less or equal to greater or equal to summation of the probability of AH, and take x belongs to s, right? And minus let's see. Sorry. I just thought it was something. So n is a random variable depending on h, right? So there's no h here. There's no h here, right? There's only, right? Because I fixed AH, I fixed AH. I already fixed h. This is probably h choose to h, right? So I want to ask AH. So I should define AH to be events that h of x equals to 0, right? So, and yeah, okay, yeah, this is true. Okay, so I pick probability of h belongs to h, and I ask the AH, okay, of x, and the union of x belongs to s. So there, you don't care about this x. But the idea is that if you pick x belongs to s, you want to ask. You want to union the events such that you put x, AH is. AH means that h of x is 0 to the k. So you want to union the x belongs to s, right? You want to union this. So this is our bound is greater or equal to x belongs to s, the probability of AH. Okay, so this A, let's say probability AH means that h of x equals to 0 to k, minus the pairwise events, right? Minus the x different from x prime, the probability of h of x equals to 0 to the k, and h of x prime equals to 0 to k. And by my assumption, right, given x, h of x belongs to 0 to the k is 1 over 2 to the k, right? So it's 1 over 2 to the k times s minus the pairwise, and by definition, this is also a constant. This is 1 over 2 to the 2k. So 1 over 2 to the 2k. And the pairwise, right? So it's s choose 2. S choose 2. Okay, so let me call this p. Let me call this p squared. So just sp minus s choose 2 p squared. Okay, and I want to compute. I only compute this, right? And I want to compute this. Okay, so I want to compute the probability of n greater or equal to 2. So this means that this means what? This means that you're asking the union bound, right? You're asking the union. You are asking the pairwise. So you're asking what's probability of h pick h and the union of all h happened, right? Because if you ask what's the union of this h, right? But you happen to be 2, right? So at least two of them should be both happen. Okay. So this is bounded by something, right? This is, so you need 2 of them. So this is, you require that 2 of them happen. Okay, so this is bounded by the union bound. So you can just summation of probability of h of x equal to 0 to k, and the h of x prime equal to 0 to k, and the x do not differ from x prime. So this is s choose 2 p squared. Okay. So so n greater or equal to 2 is bounded by this, right? Because pairwise probability is very small, right? And you at most have all of this. And but these guys somehow like this, right? So combine this, right? These guys greater or equal to, these guys less or equal to, small to less or equal to. So you can get the probability of n greater or equal to 1 is at least with the ps minus 2 s choose 2 p squared. Okay, so so this is, let's say, let's change this to be greater or equal to sp minus s squared p squared. And notice that our s is in the 2 to the k minus 2 and the 2 to the k minus 1. So this tells me that my sp is in greater or equal to, less or equal to half, and greater or equal to 1 divided by 4. So this gives you the bound on this. You can check that this is 1 divided by 8. 1 divided by 8, right? So half. Right? So half of, right? Yeah, okay. Because this is quadratic, right? So you can find it bound. Okay, so okay, but the problem is that actually we don't know s, right, in the beginning, right? Because we cannot solve this. We don't know how many solutions of the Boolean formula. Right, but what else I can do, right? We can just randomly pick. So we can randomly pick, because we know that s is at most greater or equal to n, right? So I can randomly pick, let's say k, right, from 2, 3, 4, up to n plus 1, right? Because if I choose k to be n plus 1, then I definitely force that s equal to 2 to the n, and then s equal to 2 to n minus 1, satisfy this assignment. Okay, so I just randomly pick, and at least one of them will work, right? So at least one of them will work. Okay, so this finish your proof, right? So at least one of them will work with a probability greater or equal to 1 over a. Okay, so in the rest of case, then I don't care, right? But so at least one of them will work. Okay, so I'll combine these two, that we prove these results, right? We prove these results. Okay, basically once you prove this, then the proof of Toda theorem should be, you still need some work, but up to here, that once we have this formula, then once you prove that NP is a subset of BB to pair P, then it's very close to doing some work. Then you can prove that PH is also in the subset of BP to pair P. Okay, so see you guys in the next videos.